Transformations of the independent variable. The resulting transformation of x of t into y of t is hence called an affine transformation on the independent variable. All such transformations can be decomposed into just three fundamental types of signal transformations on the independent variable: time shifting, time scaling, and time reversal. In data analysis, transformation is the replacement of a variable by a function of that variable. For example, replacing a variable x by the square root of x or the logarithmic of x. In a stronger sense, a transformation is a replacement that changes the shape of a distribution or relationship. Transformation independent or dependent variable. The incompatibility of model errors with an assumed distribution can sometimes be remedied with the transformations of the independent variable. Non-linearities between the dependent variable and an independent variable often can be linearized by transforming the independent variables. Here, a simple and very important example of transforming the independent variable of a signal is a time shift. A simple and very important example of transforming the independent variable of a signal is time shifting. Time shift. A time shift in discrete time is illustrated in figure 1.8, in which we have two signals, x of n and x of n minus n0, that are identical in shape, but that are displaced or shifted relative to each other. We will also encounter time shifts in continuous time, as illustrated in figure 1.9, in which x of t minus t naught represents delayed if t naught positive or advanced if t naught is negative. Function of x of t. Signals that related in this fashion arise in applications such as radar, sonar, and the seismic signal processing, in which several receivers at different locations observe a signal being transmitted through a medium, water, rock, air, etc. In this case, the difference in propagation time from the point of origin of the transmitted signal to any receiver results in a time shift between the signals of the two receivers. Signals that are related to interpretation arise in applications such as radar, sonar, and seismic signal processing, in which several receivers at different locations observe a signal being transmitted through a medium, water, rock, air, etc. In this case, the difference in propagation time from the point of origin of the transmitted signal to any receiver results in a time shift between the signals of the two receivers. The second basic transformation of the time axis is the time reversal. For example, and I illustrated in figure 1.10 the signal x. The signal x of minus n is obtained from the signal x of n by subtraction about the n equal to 0, that is by reversing the signal. Similarly, as depicted figure 1.1, the signal x of minus t is obtained from the signal x of t by a reflection of t equal to 0. Thus, if x of t represents an audio tape recorder, then x of minus t is the same tape recording playing backward. And the transformation is that of time scaling. Time shifting to next. Now time scaling. In figure 1.12, we have illustrated three signals x of t, x of t, and the x of t by 2 that are related by the numerical changes in the independent variable. If we again shifting of the example of x of t, the tape recording, then x of t is equal to recording played at twice the speed, and the x of t by 2 is the recording played at the half speed. It is often interesting to determine the effect of transforming the independent variable of a given signal x of t. To obtain signal of the form x of alpha t plus beta, where alpha and beta are given numbers, such transformation of the independent variable presents the shape of x of t, except the resulting signal may be linearly stretched if mod alpha is less than 1. Linearly compressed is 1. Mod alpha less than 1. Linearly compressed if mod alpha is greater than 1. Reverse in time if alpha is less than 0. Shifted in time if b is non-zero. This is illustrated in the following examples. Here x of n is IRT, here x of n, here for this x of n like this. X axis as here till n, here display time frame is related by time shift. Here time shift. This figure NO is greater than 0, so that x of n minus n naught is delayed version of x of n, that is, each point of x of n occurs later in x of n minus n0. Actually, here shifting process. This one going to here. So this one only here. So up to here. So this this one. Here n naught. Here n only. Here this position minus n naught. So here n minus n naught shifted. Transformation of the independent variable. Here continuous time signal related to by time shifting. So that x minus x of t minus t0 is an advanced version of x of t, that is the point in x of t occurs at a later. So x of t minus t0. Here discrete time signal x of n is reflection x of minus n about n equal to 0. X of n. Here x of n minus x of t. Okay. Continuous time signal x of t is reflection x of minus t about t equal to 0. Yeah, this is reflection. So x of minus t. Reflection of x of x minus t. About t equal to 0, you can say mirror image also. Okay. Here, continuous time signal related by time scaling. Here, x of t in x equal to t. Height is the x of t. Here, time also degree, but x of 2t. Continuous related by time scaling. Here, this one. Here, t by 2. Here, 2t. Example, given the signal x of t shall integer 1.13 signal x of t plus 1 corresponds to an advance pushed to the left by 1 unit along the t-axis as illustrated in figure. Specifically, we know that the variable x of t at t equal to t0 after in x of t plus 1 at t equal to t0 minus 1 or here 0, 1, 2 x of t shifting property x of t plus 1 minus 1, 0, 1 x of minus t plus 1 here x of 3 by 2 to t 2 by 2. So the convenience time signal x of t is example 1.11 to 1.13 to reach a transformation of independent variables. The time shifted signal x of t plus 1. The signal x of minus t plus 1 obtained by time shifting and the time reversal. The time scaling signal x of 3 by 2 into t and the signal x of t by 2t plus 1 obtained by time shifting and the scaling. Example, the value of x of t at t equal to 1 is found in x of t plus 1 at t equal to 1 minus 1 equal to 0 also, since x of t is 0 or n is less than 0, we have x of t plus 1 0 for t is less than minus 1. Similarly, since x of t is 0 for t is greater than 2, x of t plus 1 is 0 for t equal to 1. Let us also consider the right signal x of minus t plus 1 which may be obtained by replacing t with minus t and t plus 1, that is x of t plus 1 is the same time reverse version of x of t plus 1. Thus, x of minus t plus 1 may be obtained graphically by reflecting x of t plus 1 about the t-axis as shown in figure 1.13 into t. Example, given the signal x of t shown in figure 1.13a, the signal of x minus x by 2 into whole x of 3 by 2 to t corresponds to a linear compression of x of t by factor of 2 by 3 as